The title of my thesis is Short-Term Load Forecasting Method Based on Full Convolution Deep Learning. The traditional load forecasting methods cannot take into account the time and space characteristics of load data at the same time, which leads to the low application efficiency of load forecasting methods. In order to solve this problem, a short-term load forecasting method based on full convolution deep learning is proposed. Preprocess the power load data, delete the abnormal samples, unify the load data format through normalization processing, design the relevant network parameters, determine the loss function, complete the design of the prediction model, use the sample data to train the prediction model, and predict the short-term power load after the model meets the prediction requirements. The experimental results show that, in the same experimental environment, the short-term power load forecasting method based on full convolution deep learning has high prediction accuracy, wide prediction range, and its application efficiency has been improved. Power system load forecasting is based on the historical data of power sector, economy, policy, meteorology, etc., to explore the influence of the historical data, change characteristics of power load on the future power load, and define the possible relationship between power load and various related factors, so as to correctly predict the future power load. According to the length of forecasting time, power sector load forecasting can be divided into annual forecasting, monthly forecasting and daily forecasting, as well as long-term, medium-term, short-term and ultra-short-term load forecasting. The coverage time of long-term forecast varies from the next few years to more than 10 years, which is mainly used for power development planning and power grid development planning. Medium-term forecast refers to the power load forecast in the next year, which is used to arrange the overhaul plan and the economic operation of hydropower plants. Short-term load forecasting usually refers to the daily load forecasting in the next 24 hours and the weekly load forecasting in the next 168 hours. The goal is to arrange daily and weekly power generation tasks for each power plant, including the determination of unit startup and shutdown, coordination of thermal power and hydropower, fuel procurement and supply, tie-line exchange power, economic distribution of power load, reservoir dispatching and equipment repair, etc. Ultra-short-term forecast refers to the forecast of 1 hour, 0.5 hour or even 10 minutes in the future, which is mainly used for safety monitoring, preventive control and emergency handling. Among the various attributes of historical load data and historical meteorological information, the data may be abnormal due to the unknown records or abnormal events. These data not only have no reference value for forecasting itself, but also affect the load forecasting results to a large extent. Therefore, it is necessary to determine which abnormal samples are and exclude them from the data input. The following abnormal data detection algorithm is based on the combination of distance and clustering. Firstly, the samples are divided by clustering algorithm. Secondly, for each sample, calculate its clustering distance, and then calculate its anomaly index. Then all samples are arranged in descending order according to the size of the anomaly index. Finally, the sample with the largest outlier index is determined as the outlier sample. The prediction model design combines the full convolutional neural network and uses several parallel U-net neural networks to process short-term power load data. The structure of the full convolutional neural network is shown in Figure 1. The whole structure of the neural network includes 3 parts: downward contraction path, convolution LSTM module, and upward expansion path. The main function of contraction path is to learn and extract important features from the input data. Convolution LSTM layer receives features and fuses the adjacent features of y-axis to enhance and improve its own features. After expanding the path, the predicted data block is obtained. Because the y-axis dimension of the input data block is 8, The proposed neural network is equivalent to 8 parallel UNet neural networks. It is proposed that the shrinking path and expanding path of neural network consist of 3 different levels of shrinking module and expanding module respectively, and the characteristic dimension and channel number of different levels of modules are different. Each shrinking module contains a residual module and a pooling layer. Each residual module contains 2 convolution layers, with the size of 3*3 convolution kernel. The convolution layer uses the strategy of filling zero value to avoid dimension reduction. Each convolution layer is followed by a back-H normalization layer and an activation function. The template size of pooling layer is 2*2, and the maximum pooling strategy is adopted. Every time the pooling layer passes through, the number of channels of the next feature is doubled. More feature channels can get more multi-SC-AL features. The number of channels in the 3 levels of contraction path is 32, 64 and 1280 respectively. The convolution LSTM layer is located between the contraction path and the expansion path. This algorithm uses 2 bidirectional convolution LSTM layers with 256 channels. This structure effectively connects 8 parallel UNet neural networks in series. The features extracted from different UNet after shrinking path interact and fuse in convolution LSTM layer to improve the segmentation effect of network. There is a convolution layer with the size of 33 convolution kernel between 2 bidirectional convolution LSTM layers. The features enhanced by convolution LSTM layer will be sent to the expansion path. The expansion path and contraction path are just opposite. It includes 3 expansion modules. Each expansion module contains an upper sampling layer and a residual module. The structure of each residual module is the same as that of the shrinkage path. The upsampling layer is equivalent to the reverse process of the pooling layer, and the template size is also 22. The maximum strategy is adopted. Every time it passes through the upsampling layer, the number of the next channels is halved. The number of channels in the 3 levels of expansion path is 128, 64 and 32 respectively. Like the original UNet structure, this network also adds 3 jump connections to connect the same level of contraction module and expansion module. It is helpful to learn segmentation details. Finally, 11 convolution layer is used to reduce the dimension, and a 3-channel characteristic graph matrix is obtained. Finally, softmax layer is used for classification. Softmax layer can classify the known data. Before the prediction, the bottom-up unsupervised pre-training is used to initialize the parameters of the full convolution neural network, and then the top-down supervised training is used to fine-tune the parameters of the whole network. The connection weight and bias of the visible layer and the hidden layer and the model are continuously adjusted to fit the functional relationship between the input and output data. Then the overall cost function of the prediction model is as follows. The Hadoop cluster built in the experiment consists of 6 PCs with the same configuration. Each PC has 2 grams memory, sub hard disk, dual-core Intel i7-500 CPU, 293 GHz main frequency, and runs several CentOS Linux operating systems. One machine is the master node of master, which is responsible for the resource allocation and job scheduling of the whole cluster. The other 5 machines are slave nodes, which are mainly used to store data and run tasks. If the number of HDFS copies is 3, the slave node can run 4 MapReduce tasks at the same time. The Hadoop cluster topology is shown in Figure 2. The experimental data comes from the load data and influencing factor data collected by a power grid in a certain area. The amount of data is TB level, and the latitude is high. It is mainly structured and semi-structured data, which is in line with the characteristics of power big data. The influencing factors include daily maximum temperature, average temperature, minimum temperature, average wind speed, average humidity, average precipitation, sunshine type and season. In the experimental environment, Different load forecasting methods are used to forecast short-term power load. The coverage area of load data processed by each forecasting method is calculated, and the experimental results are output through the third-party software. The specific content of load forecasting coverage area experiment results is shown in Figure 3. Through the observation of Figure 3, it can be seen that the three traditional load forecasting methods cannot cover all load data when processing load data. There are some missing data points outside the distribution point. Compared with the above, the proposed load forecasting method covers a larger area and covers all load data. According to the experimental results of prediction accuracy, the load forecasting method based on full convolution depth learning has high prediction accuracy and high application efficiency, which is better than the traditional load forecasting method. Load data has dual characteristics of time and space. In terms of time, load data has the characteristics of long-term trend, periodicity and close association with its own historical data. Because the load data has these characteristics, the algorithm model can fit it well. In pace, the operation of power system is affected by external factors, and the load data produced also has the characteristics of randomness. According to the characteristics of power load data, after the design of the short-term power load forecasting method based on full convolute and deep learning is completed, the experimental environment is built, the load data is collected, and the prediction accuracy and prediction area are compared by using different prediction methods. According to the two groups of experimental results, it is proved that the prediction method based on full convolution deep learning has higher accuracy and wider application range. It is suitable for practical projects. However, there are still some deficiencies in the design process. In the follow-up study, some shortcomings of this method will be studied and analyzed one by one to further improve the load forecasting method. Thank you very much for listening.